All right, so next part of our setup here was to calculate the pH after 150 milliliters of the sodium hydroxide was added. Now, and we determined that the equivalence point was at 250 milliliters. So it's important to note that this is a volume that is before the equivalence point. So we still have we still have measurable amounts of the weak acid and its conjugate base in the solution at that point. And now there's a hint. So you've got moderate concentrations of measurable concentrations of both a weak acid and its conjugate base. So we essentially have a buffer solution, and that's why this intermediate range is often called the buffer range. And the way that we calculate the pH at any particular point along that in that range is very much how we calculated the pH of a buffer solution after the addition of some acid or base. So to review, this is going to be a two-step process. You've got the stoichiometric reaction between, in this case, the strong base, hydroxide, and the weak acid. So because one of the pair is strong, in this case the base, the reaction is complete. And use that to calculate how much of the acid was reacted away, how much of the base was made, and then get new values, and then use Ka, Hx, and use the Ka reaction to determine the hydronium concentration, and then by extension the pH. So this is almost exactly like the buffer example. So first, let's calculate the new concentrations of the propionic acids before the reaction. So this is a setup that is very similar to what we did with the base as far as the making a reaction table, but not a nice table. All right, but first let's get the amounts that we have here. So we had 100 liters of the, or 100 milliliters, or 0.1 liters of the acetic acid. It was 0.5 moles per liter. So that means that initially, before we did anything, our flask had 0.05 moles of the acetic acid in it, which means its new concentration would be less. Remember, we have this acid was initially contained in 100 milliliters. We have at this point added 150, hypothetically. So it's a bit diluted. So now the new concentration is 0.2 molar. Hydroxide. So the amount of hydroxide we get from the amount that was titrated into the acid, which you were told at this point was 150 milliliters, 0.15 liters. And its concentration was 2 moles per liter, which means that we have 0.03 moles. So the new hydroxide concentration at that point would be 0.12 molar, taking into account the dilution. Now remember that this is fairly hypothetical because you can't mix them and not make them react, but for calculating these numbers, it is a legit thing to do. So here is our stoichiometric reaction. So the acetic acid reacts with the added hydroxide to form acetate and water. And so this is going to be a reaction table here. So the amount of all of these species, after you've mixed them together, but before they react. So we've got 0.05 moles, no acetate, 0.03 moles. Now, the next item in this reaction table is the change, assuming complete reaction. All right, so we have way more hydroxide than we do acetic acid. So it's going to run out because they react 1-to-1. All right, so we're going to lose the 0.3, end up with no hydroxide. We're also going to lose 0.3 moles of the acetic acid, which will give us 0.02 moles at the end. And the acetate we're going to gain, we had none, we added 0.03 moles, which means we now have 0.03 moles. All right, so this is the amount of acetic acid, acetate, and hydroxide that are present after you have added the hydroxide and given them the millisecond that they would need to react. Next, to determine the pH, again, this is the equilibrium that's going to tell you what the pH is, because this is the one that creates the hydronium, and it's the reaction of the acetic acid with water. And this becomes now you can do this a couple of ways. You can do the full-on ice table using these amounts. You would convert them to concentrations, and using those new concentrations, you could work out the ice table, but you could also be a little more clever. And because you've got a buffer solution at this point, because you've got measurable amounts of both the acid and the conjugate base present, you can use the Henderson-Hasselbalch equation to solve the pH at this intermediate point. And that's what this looks like. And this looks ugly, but it's really not. So here's the basic setup. pH equals pKa plus, ignore that extra plus sign, log of the base concentration divided by the log of the acid concentration. Get rid of this one. Fix these as well. And here we can symbolically, now in theory, even this is redundant, because these are the concentrations. So these are going to be the amounts that we have of these species remaining divided by the volume. But it's just a ratio. And the ratio of the amounts and the ratio of the concentration is exactly the same. So you wouldn't even actually need to explicitly write in these new volumes here, but I did it for the sake of completion. And once you plug everything in, fingers crossed, you should get a pH of about 4.92. Does this answer make sense? It's higher than what you started with, so there's at least that. And for those of you in lab, you're beyond the halfway point, which means that the pH should be greater than pKa, which in fact it is. But this is the sensible answer, and so this would be the pH at the intermediate point of having added 150 milliliters, when 250, I think, was the end point for here.